So we're in a chapter on gas power systems. The first part is internal combustion engines. We've covered the Otto cycle, and today I would like to cover the diesel cycle. Both of the Otto and the diesel mimic what you have available for purchase in vehicles like trucks and cars. You can get a diesel engine or you can get a gasoline engine. And so that's what they're trying to simulate. Both of them are 4-stroke. And you analyze or make an analysis of the 4-stroke cycle engine really with just 2 strokes of compression and then the power stroke, and you replace the other 2 strokes with heat transfers. What we're showing here is the piston at bottom dead moving to top dead. As you compress it, it changes color. It's showing it's warmer. Then here for the Otto at top dead center, there's combustion. Now it's really hot, high pressure. You undergo a power stroke, and then you undergo heat transfer to reject. So heat addition at constant volume, and then heat rejection at constant volume. That's our Otto cycle. What I was going to do before I cover the diesel is show a quick video clip on the comparison of the Otto and the gasoline engines and diesel engines. So let me do that.
Gasoline and diesel engines are the 2 most commonly used internal combustion engines. Even though their operations seem similar, they have some interesting differences, and each has advantages over the other. This video is aimed at exploring these differences and advantages from a scientific point of view. Both engines have the basic 4 strokes.
So hopefully that was illuminating. I think sometimes I can say it in words, but if you see it in pictures and somebody's saying it at the same time. So the volatility of gasoline, much higher than the diesel. And let's jump back to the lecture. Also, anybody ever put the wrong fuel in the wrong engine or the wrong gas tank? So a friend had a diesel and put gasoline in and just not thinking at the pump. And it's an expensive bill to pump it all out and purge it. And then another story that I have is one of my distant relations owns a company, and he has a fleet of vehicles, and he had his own gas tanks, and he had diesel tanks and other gasoline tank. And he noticed that he suspected some of his employees were filling up their vehicles before they went home, which is a no-no. So what did he do when both tanks went out? He just told the guy, just put the diesel in the gas and the gas in the diesel this time. And when the employee called in saying that my girlfriend put the wrong fuel in my car, he had the sheriff over, and that was not so good for the ex-employee for that. So anyway, let's talk now about the diesel cycle. The first process, 1 to 2, is the same. It's adiabatic compression. So on a PV diagram, you'll start, it looks like that. But what you're going to do is you're not going to just compress it 10 to 1. You're going to compress it like 20 to 1. And you're not compressing air-fuel mixture. You're compressing just pure air. So it gets much higher pressure because it's a smaller volume. And then you don't have constant volume heat addition. The fuel is less volatile, and as you're spraying it in, the approximation in the diesel cycle is that you're starting to go and expand at constant pressure. So it's a constant pressure heat addition from state 2 to state 3. How did that compare with the Otto? Otto was very fast. Heat added, so they just said constant volume, all the heat's brought in. But the diesel, much slower combustion, you're spraying it in with the fuel injector, so it's constant pressure is the approximation. But then you cut off the fuel, and you're still expanding in the power stroke, and so you'll come down to state 4. And then at in the approximation of the diesel cycle, you'll then replace that intake exhaust and intake with just a constant volume heat transfer. So this is the big change right there, the constant pressure heat addition. What did we have? We had a compression ratio, R as the symbol. Was that V1 divided by V2? Is that our definition of the compression ratio? Okay. Well, you see we have another V. This is V3 now. And so what happens is we have another ratio, and it's a ratio of the volumes, and it's called the cutoff ratio. So RC, the subscript C, cutoff. And it's V sub 3 divided by V sub 2. Maybe that's 1.5, maybe it's 2, maybe it's 2.5, something, but it's not really big. Okay, it's just a few. It's not like it's 10 where you're spraying in fuel for that much change. So this is the cutoff ratio. Sometimes I find that a little difficult for me because other textbooks that I've used for different classes, they'll say compression ratio, C for compression. Oh, they'll put a C on that. And this book doesn't. So the compression ratio has no subscript. And the cutoff ratio has a subscript C for cutoff. All right. Well, we want to analyze this system. And so the first law for the process 1 to 2 isn't any different, is it? And in the compression, is there any heat transfer from 1 to 2? No, so that's 0. And we could calculate the work 1 to 2 from the first law. It'd be something like minus U2 minus U1, and if you have a constant specific heats, it'd be minus C sub V T2 minus T1. That's all good. We've done that before. But the big difference is constant pressure, heat addition from state 2 to 3. So if I look at the first law for the process 2 to 3, is Q 2 to 3 0, or is work 2 to 3 0, or are any of them 0? None of them are 0. So, now, is there an easy way I can calculate the work 2 to 3 though? Boundary work, it's pushing, it's expanding, it's pushing down that piston or pushing back that piston. So the work 2 to 3 is the integral P dV from 2 to 3. And since the pressure is constant, it comes outside the integral. And so we have the pressure times the final volume, V3, minus the initial V2. Sometimes they'll write it like this. They'll write P3V3 minus P2V2. Is that the same? It's exactly the same because P2 is equal to P3. But they wrote it that way because you have, going back to the first law right here, you have U3 minus U2 equal to Q2 to 3 minus P3V3 minus P2V2. What do you think they do with that pressure volume terms? Rearrange it. What side did they put it on? Put it on the other side. And when you put it on the other side, you get H3 minus H2 equal to Q2 to 3. What is the definition of H? U plus PV. So that's a definition of enthalpy. This is one of those rare cases where enthalpy shows up in an equation legitimately for a closed system analysis. Almost always we use enthalpy for open systems. It's what flows across the boundary in and out of our system. And why do we have it? Because we have flow work incorporated with that enthalpy. Okay. So this also looks very funny to students when they see this. They'll say, I understand the Otto cycle, but when I get to the diesel cycle, some of these, they have enthalpy, some internal energy. I get confused. Well, you just have to study it and understand why now in the process from state 2 to 3, Q is not equal to a change in U like it was for the Otto cycle, but Q is equal to a change in H, the diesel cycle. All right. What about this term right here from the law, first law from state 2 to state 3? 3 to 4. Well, it's just like we did for the Otto cycle. Isn't the Q 3 to 4 equal to 0? Sure. And so the work 3 to 4 is equal to the change in internal energy. So let me expand that a little bit over here. So the work 3 to 4 is equal to minus U4 minus U3. Is that true? Did I mess it up? Does it look good? And this, using constant specific heats, would be minus C sub V T4 minus T3, or if you want to get rid of that minus sign, switch the order, T3 minus T4. But how would we normally calculate this temperature at the end of the expansion? Well, it's isentropic, S equal to constant, from state 3. And so normally it would be like T3, 1 over the compression ratio to the K minus 1. Are you familiar with that? Right? So you had to solve an Otto problem. You're using that ideal gas relation, constant specific heats, isentropic process, how temperature and volume are interrelated in an equation. Well, here we're not going the compression. What we're doing is we're expanding, and so there's the change right in here. It's not the volume at state. It used to be the volume at state 4 minus the volume at state 3. It still is that, but that's not the compression ratio, is it? So what we do is we put T3 and we put V3 divided by V2 times V2 divided by V4, all to the power K minus 1. And now we see that, oh, this part right there is 1 over the compression ratio. But this part right here is the cutoff ratio. So we have the product of the cutoff over the compression ratio raised to the power K minus 1, and that's how the temperature 4 can be predicted from the temperature 3. That look good? Okay. All right. So that's a difference right there. And then 4 to 1, well, the work 4 to 1 is 0. So let's move on. You can derive this equation for the thermal efficiency of the diesel cycle. It's outlined in the textbook or other textbooks. I made a video of it, put it up. You can watch it. In the interest of time, I'm going to encourage you to review the video, review the textbook, and it's just like we had the thermal efficiency for the Otto. Do you remember that? 1 minus 1 over the compression ratio to the K minus 1? Just like that. But for the diesel, you get this term in square brackets right there that come in and are an additional modification to the basic structure of the equation for the thermal efficiency. And the thermal efficiency of the diesel, a function of not only K and the compression ratio, but also the cutoff ratio. The cutoff ratio R sub C. We're going to set up and solve a problem. So we want to analyze a cold air standard analysis or perform a cold air standard analysis of a diesel cycle using this value of C sub V and this value of C sub P. Notice, did they give you K in that first sentence? Yes. They gave it implicitly because they gave us C sub P and C sub V, and you just take the ratio, and that's how you calculate K. C sub P over C sub V. Okay, air at a given temperature and pressure are at the start of the compression stroke. And the compression ratio is 21, and the cutoff ratio is 2.5. and they want to know the temperature at the end of the compression stroke. So quickly you want to make a sketch again on the PV diagram. Here's 1 to 2 to 3 to 4, down again. 1, 2, 3, 4. You could also make the TS diagram sketch as well. It'll just look like temperature entropy. 1 to 2, 2 to 3, 3 to 4, 4 down to 1. Now, so what is the temperature at the end of the compression stroke? We're asked to calculate T2. What is the peak pressure? Well, that's P2, isn't it? It's also equal to P3. What is the peak temperature? That's T3. What is the heat addition for the cycle? Well, you're bringing in the heat in the process from 2 to 3. So isn't that Q 2 to 3? And then what is the net work of the cycle? That's W net. And then the thermal efficiency. The thermal efficiency is going to be the ratio of W net divided by Q 2 to 3. I encourage you to set up a table of properties. So we'll have state 1, 2, 3, 4, the pressure at the state, the temperature at the state. You really don't need the specific volume, but you could put it in if you like. They gave us the temperature to start with, 310, and the pressure, 98 kilopascal. And how do I calculate the first unknown, T2? Would it be T1, compression ratio to the K minus 1? Would that work? It would. All right. And then how about the pressure at state 2? Would that be P1, compression ratio to the K? And so you start filling these in as you go through the system. Once I know P2, I know P3. It's the same. But how do I get T3? How do I get this temperature at state 3 at the end of the constant pressure heat addition? You always remember at any point, any time in the cycle, it's always behaved as an ideal gas, does it not? And so you have that P2 V2 divided by T2 is equal to P3 V3 divided by T3, true? And in this case, the pressure 2 is equal to pressure 3. And so the temperature at 3, maybe I just write it up here, is equal to the temperature at 2 times V3. V3 divided by V2. So it's equal to R sub C, the cutoff ratio, times the temperature at 2. A little bit of work to establish that relation, true? So we get that. And then we just covered how to find T4. So T4 is equal to T3 times the cutoff ratio divided by the compression ratio to the K minus 1. And then the P4 is just like that. I'm using up valuable space here. So let me try and draw it over here. P4 is equal to P3 times the cutoff to the compression to the K. What you really want are these temperatures, because once you have the temperatures, you can use to analyze each of the heat and work transfers during the processes. So for process 1 to 2, 2 to 3, 3 to 4, 4 to 1, I want to calculate the Q in kilojoules per kilogram and the work in kilojoules per kilogram. First things first, let's identify which ones are 0, right? So for adiabatic compression, 1 to 2. How about nothing is 0 for either Q 2 to 3 or work 2 to 3. But how about 3 to 4? Q is 0. And then the work 4 to 1 is 0. The others are non-zero. Okay. Let's just think about the sign. This first work is going to be positive or negative for the work 1 to 2. Negative, exactly. How about the heat transfer 2 to 3? Positive. Good. How about the work 2 to 3? Positive. How about the work 3 to 4? Positive, right? And then the last one, the Q 4 to 1? Negative. And then when we go ahead and do the sum, and this is Q net, and this is work net, I have 2 non-zero terms for Q. I have 3 non-zero terms for work. Will Q net still equal W net? Yes. It definitely will. It definitely will. Okay? All right. So, I think a lot of these you already have. The work 1 to 2 is the change in internal energy. So it'll be minus C sub V T2 minus T1. Done that for auto, nothing different. You can get the Q 2 to 3, C sub P, constant pressure, because it's a change in enthalpy. It'll be T3 minus T2, as well as the work 2 to 3. Well, you said that was the integral PDV, and so is P3V3. It was P3V3 minus P2V2. But PV is always equal to R times T. So it's R times T3 minus T2 for the work 2 to 3. I'm using the ideal gas equation there. Does that make sense? All right. That's a bad looking P3, isn't it? That's equal to P3V3. All right. Minus, okay. The work 3 to 4 is very similar. You have C sub V times T3 minus T4. And then the last Q 4 to 1, C sub V T, well, let's put a, depending on how you want to write it, but it'll be T1 minus T4 will give you the right sign. All right. Here are the numbers for that problem, so you can take a look at it. Yes, sir. Okay. Okay. And so, again, these are zeros on the heat transfers. This is 0 on one of the work. We have a negative, 2 positives. You do the sum. You do the sum for the net Q in of the cycle, the net work out of the cycle, and they're equal. And then you can calculate the efficiency, and it's very high because it's an analysis, you know, but it gives us the right trend for the numbers, 63%. If you use the cold air standard equation to calculate the thermal efficiency, that single equation, knowing the cutoff, compression, and K, wow, you get the same number, which is good. This is good to see that. You could also calculate the mean effective pressure if wanted, but it wasn't asked for in part A, B, C, D, E, or F. Look good? All right. Let's talk a little bit about gasoline. We talked about it last time. What was the key index number? And you pay for higher price for higher grade gas? Yeah, it's octane. So in the United States, we use an anti-knock index, which is the sum of the research plus the motor divided by 2. All right. So, but what about diesel fuels? Well, instead of an octane number, we use a cetane number, and it's a measure of the fuel's time of self-ignition or ignition delay. So if you put it at that temperature in an air mixture, it'll combust, but a lot of times it takes a little time before it combusts or starts the combustion process. And so that's the ignition delay. And if you have a higher cetane number, it has a shorter ignition delay, which is better. But once you're over a number, you don't have choices at the diesel pump, do you? There's not like cetane of 40, 45, or 50, like the octane number. And sometimes you don't even see that number posted. What you'll see is something like this is number 2 diesel. That's what you'll see. And so typically there's not any variability in the purchasing of that fuel. If you are a long-haul trucker and you're going to Alaska or somewhere up north in the middle of winter, and you're going to shut that engine off and then want to start it a couple days later when it's super cold, you may put some additives in your tank of diesel, just like you probably put some additives in your tank of gasoline, right? But other than that, there's no big variation at the pump for quality or of diesel. Let me show this video which explains the cetane number and how it impacts combustion.
The cetane number of a diesel fuel is critically important to combustion. But how does it really impact what is going on in the engine?
And also I took a look at Ford. They make a lot of big pickup trucks, and you can get the owner's manual online for a lot of F350, F250 trucks that have the diesel engines. And I said, I wonder if they specify a minimum cetane number, like there's a specification of a minimum octane number in a lot of automobiles. Well, I read through and I copy and paste it out, and here it is. It just basically says you need to use low sulfur diesel. There's an acronym for it, designated either D1 or D2, and the 15 ppm sulfur. So that's the maximum sulfur content. And if you remember, maybe you're too young or whatever, there was a price jump in diesel when that federal regulation came into play, just 5, 6, 7 years ago. I can't remember, maybe less than 10. And because they used to not regulate the sulfur content that stringently, and then they moved it to 15 ppm, which increased the refining costs. Also, if you continue to read, you can operate your vehicle on diesel fuels containing up to 20% biodiesel, called B20. But I thought this was interesting. It's in the manual, just like this. Do not use home heating oil. Do not use agricultural fuel. Do not use raw fats and oils or waste cooking greases or biodiesel fuels greater than 20. There's a lot of stuff you can throw in your diesel tank and still work. And also, do not add gasoline, gasohol, or alcohol to the diesel fuel. That's in the manual that I found, the owner's manual. So, but nothing, not a word about the cetane number. This one I'd like to show you. They talk about the gasoline engines having a spark plug and the diesel having a fuel injector. But things are changing in your lifetime. In this Bosch video that they put out a number of years ago, they even talk about the number of vehicles which will be gasoline direct injection by the year 2020 or something like that, which isn't that far off, is it? Does anybody know if they have seen a gasoline direct injection ignition? You have? Anybody else? 3, 4? As I continue to teach next semester, there'll be more of them because you can buy them. They're made. Do you remember your manufacturer? What do you have?
It's a Volkswagen Passat.
Okay, Volkswagen. Anybody else? Do you remember?
Direct injected motorcycle.
Direct injected motorcycle. Do you remember what manufacturer? Yamaha? What did you? Volkswagen? Volkswagen, okay. Another reason, this video is a little longer, sorry, but please watch. But it's I think has a good graphics just on engines and drivetrains. So I'm going ahead and play that. We'll go ahead and stop there. This was probably one of the best that I've seen, a couple of them. Really shows you all the components without having to get your hands dirty and inside an engine. So let me jump over here. There's another one I'm not going to show you, but this is a common rail diesel system. Does anybody remember when diesel engines were really loud? They're clack, 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 clack. Yeah. And then why did they get quiet? Engineers really worked on it. And they have a little pilot burst of fuel because they can have a different way of having all that fuel rail is high pressure fuel ready to go to any one of those. It used to be the injector was right there. And it kind of popped it in and made the high pressure right before it pushed it in, but that's old. So a common rail system also with electronics and give a little burst of fuel to get it such that when you give it the main burst of fuel, it's already a hot fireball already there. And before it would say, okay, now let's start combustion, throw it in, it's kind of cold even though it's 20-to-1 compression ratio. And then it was a lot of big drops sprayed in, not as high a pressure, not as fine a mist, and then you had multiple burnings going on at different pockets, and it was a lot louder clanking, needing a lot stronger crankshaft bearings and other things. So there's been a lot of innovation the last 10 years. And let me jump over here and encourage you to take a look at that. Thank you very much.